Hi. Let's see. Yeah, I wanted to address your excellent question from last time. I was mistaken. I'm not afraid to admit it. What I read in the book, what I thought was referring to it, it wasn't that. That's okay. I thought over it, and you asked, we went over Newton's second law, how F net, the net force, is equal to a mass being accelerated. And then it seemed like I turned right around and just said, well, let's just pick F and figure out weight. So I wanted to explain that a little better. That's where I'm going to start. So Newton's second law. We figured out that acceleration is proportional to two things. The force but the mass matters as well, how much inertia the thing has. And yes, I am intentionally being redundant. The more you push on something or pull on it, yes, the greater you'll change its motion. The more inertia it has, the more it will resist that change. Put that together, and that's what Newton's second law reminds us of. Ah, great. So you can rearrange it algebraically. And I think what might clear up some of the issues that came up last time, which I think was a great insight, by the way, was if you just add net onto these accelerations, you'll never go wrong. Or at least I tried to think of one last night. Because that's really what it means. I just haven't been emphasizing it. You have to think of all the net force. Basically, you're looking at an object that's either at rest or in motion, and you want to see if it's going to change its motion. In order to do that, you have to consider everything that's acting on it. That's what I've mostly been emphasizing, the F net. Whether there's air resistance, friction, or not. It will help you out. Well, what that results in is the change in motion of the object. Is it going to accelerate or not? We got into weight due to gravity last lecture. And you look at, here's a good example, the coffee filter. The force acting on this due to gravity accelerates it down. Air resistance acts on it upward. And so it's net motion. I mean, let me say it as those two forces combined to be F net. Tell you what the coffee filter, the object's acceleration, really is. What is the coffee filter's acceleration right now? As soon as I let go of it before it gets to terminal velocity, what's its acceleration? Say again? We have a vote for 10 meters per second squared. Any other votes? As soon as I let go of it, but before it gets to terminal velocity. Your clue is before it gets to terminal velocity. What happens at terminal velocity? What's its acceleration? 0. Terminal velocity, that means it's constant velocity. It is no acceleration. So something is happening to the acceleration. Is this helping you? So again, what do you think its acceleration is right after I drop it, but before it gets to terminal velocity? And another clue then, since you're not is not 10 meters per second squared. Kate?
Well, one place the book talked about if it was less than a second, it would only be 5 meters. It would be only going 2 meters. There was one place.
Yeah, you're right. That's the key. If it starts at 10 meters per second squared, as soon as I let go. When it gets to terminal velocity, most of you just said the acceleration is 0. So it must be decreasing through that time period, becoming less and less than 10 meters per second squared. Some of you are going, well, I thought you wanted a number. I didn't specify. I was just hoping you got that noticed it was less than 10 meters per second squared. It was decreasing. And I didn't emphasize this well enough. That's the net acceleration of this. We want to know the motion of this thing. And is its motion changing? In this case, yes, because there's an acceleration on it. But the acceleration is not only due to gravity. We looked at the force due to gravity, but we also look at the force due to air resistance. Each of those independently are trying to accelerate this in opposite directions. So we can easily think of that then as, oh, there must be a net acceleration. There's an acceleration down due to gravity and an acceleration up due to air resistance. We get this net effect. So in this case, again, from here to about there, it's something less than 10 meters per second. Yes, I saw a hand. Oh, yeah. So my point here, if you always, in Newton's second law, we're looking at an object, and I hope it makes sense to you that we have to consider everything acting on it to know whether or not its motion is going to be changed. And if it is, that's going to give us the change in motion that we're actually seeing. Thus, your book then went into, what if we wanted to find out what the acceleration was on this coffee filter just due to gravity? The Earth is pulling on that. It's trying to accelerate it downward. Can we figure out just that? Sure, we know this is accelerating less than whatever that value is, but can we determine it? Sure. That's when you can okay, I'm not figuring out the net motion of this thing just due to gravity. So just put in the force due to gravity, and that'll give you the acceleration just due to gravity. Does that make sense? Which, of course, we learned was g negative 10 meters per second squared. We already know that. But you could likewise do the exact same thing. Let's do air resistance. If we want to know what the acceleration on that thing is upward just due to the air resistance, we'll just plug in that force. That's the fun part about this relationship. And we can figure it out. So you can see the difference between this A and this A give us this net A. And by definition, ouch. The force due to gravity we call weight, which can you see on Earth, our mass times the acceleration due to gravity. So common when we live on Earth, we give it its own letter, g. So weight is a force, but it's the force just due to gravity. And that is different than mass. Mass is not a force.
Since you brought this up, I'm going to ask a question about number 2. I remember the book saying if they talk about weight, they're talking about weight on Earth. So it's taking into consideration gravity.
If they're talking about weight, they're talking about weight on Earth, okay?
It says gravity on the moon is only 1/6 as strong as gravity on the Earth. What is the weight of a 12 kilogram object on the moon and on the Earth? So is that the weight?
Yeah. Yeah, they're comparing the gravity on the moon with the Earth. And so if you're 16 kilograms, let's just start with that. 16 kilograms is referring to what? The mass. Kilograms tells us that because that's the unit for mass. I'll think out loud. I know there's a setting where I can set these to give different numbers for each student. When you pull it up. So that, you know, after you solve it, you can't just give the answer to somebody else. And that's probably what happened. Okay, 12 it is. I don't care. Yeah, that in that case would be this. That's mass. On Earth, if I want to know its weight, then that mass is trying to be accelerated 10 meters per second. So 120 newtons. Remember, standard units, that's what it comes out to be, as your book explains. 120 newtons down is its weight on Earth. You with me to that point?
Okay. I guess what's confusing about it is it's saying, what is the weight of a ground electron? So it seems like it should say with a mass of, or something.
That would be more complete, yes. Yeah, what is the weight of an object with a mass of 12 kilograms? That's what you'd like, right? That would be more complete. It is not necessary now that you're taking this class and learning, because kilogram is a unit for mass. Let's say the other ones, you know, grams, actually kilograms. I can't think of any other off the top of my head.
Okay, so when it says,
So yeah, that's a big tip-off.
okay, that means it's talking about its mass.
Yeah. And your other tip-off, if it says 120 newtons, ooh, that's a force. Okay, I got that. And if that was due to gravity, I know that's the weight. Yes. Thank you. Yes. Look. I've noticed the author switched, and so I did catch it eventually, and I allowed a percent tolerance on your answer. Thus, if you use 9.8 or 10, the difference that it comes out to be should be small enough, and WebAssign is supposed to be accounting for that, less not counting you wrong if you use either one. Again, due to the tolerance, it wouldn't matter. Thus, say you, well, I don't know, say your answer was 13.674. If you entered 13.7, the percent difference in those, I'm accounting for. So, frankly, I don't care. Typical, I chose not to get into significant figures for this class because I'm more worried about physics than I am accuracy. If you have numbers like this, 12 and 10, if you want to know, significant figures are 1, 2. And this one has 1, 2. Okay, the smallest amount, 2. So your answer should have 2 significant figures. Let's say you multiplied this by, let's make it easier for me, 2. That is 27. Technically, that one only has one significant figure, and so your answer is only accurate to one significant figure. So, but see, that just seems weird. Seems weird. I'm not going to go there. I would just encourage you that if you have something, you know, your calculator spits out something like this, don't enter it. That's just silly. Are we really this precise? No, probably not. Just round it up a bit, you know. But I should be taking that into. It should account for that tolerance, so it won't count you wrong.
When she was talking about the weight on Earth and stuff, would you put negative 120 or would you put 120?
Oh, yes, good question. Good question. I'm thinking that he just did positive. Yeah, yeah. WebAssign is not doing the negative sign. I would not enter the negative sign. And if we ever run across one where he's switching his convention, somebody will bring it to my attention, I'm sure, and I'll recredit. Technically, in physics, force is a vector, which means it needs a direction. That's why, well, so is acceleration. I'm choosing down as negative, and so you could say this is negative 120 newtons and be done. Or we can say it's 120 newtons down. Or what I think he's just feeling is, wait, it's implied it's down. He's not technically stating it. And so 120 newtons of weight kind of implies the direction. But I wouldn't enter the negative for that. I'll double check after class, of course. But
I had a hard time with one of the questions, number 6.
well, let's look at it now then. What the heck? Number 6.
The second part of it, asking about the apple that weighs 9 newtons. What is the net force on it after you release it and hold it up?
There we are. Okay. I printed it small. Didn't find it. What's the net force on an apple that weighs 1 newton when you hold it at rest above your head? And then part B is, what is the net force on it after you release it? I don't mind. Here, okay, here's a big fat heavy apple. We'll start with A. What's the net force on an object that weighs 1 newton when you hold it at rest above your head? And you guys would think what? I heard a lot of zeros. Is it accelerating? Is it changing its motion? So what's its acceleration? And I'll be more accurate. It's net acceleration, 0. So what's its net force? 0. Now I let go of it and it wants to know the net force after I release it. Is it changing its motion? Is it accelerating? So is there a net force? Okay, we at least know it's not 0 now, right? Well, what would it be? What's acting on it? Gravity. So, hey, let's see. It's accelerating due to gravity. G. If you multiply that by its mass, you would know the force of gravity acting on it. So the earth is pulling down on that apple with a force equal to its weight. It is its weight. That's how it gets its weight, because it's earth pulling on it, the force due to gravity. So you figure out its weight, and that's your answer. Yeah.
And the question that she just asked, I haven't seen it yet, but did she say that the apple at rest above the head was at 1?
0 when it's at rest. And then there's a second part to the question. Reread it. What is the net force on an apple that weighs 1 newton when you hold it at rest above your head? Would I do what?
Would you do the net force equals mass times gravity?
Yeah, in this case you want yeah, yes. I'll just stop babbling. You would use that formula. Because as soon as I let go of it, now the force of gravity is causing it to accelerate at that rate. So if you multiply those two together, you get that force. Force would be in newtons. That answer would be in newtons. So what we can learn here is when you're in free fall and ignoring air resistance, you jump out of your plane, Earth is pulling on you with a certain amount of force. How much force? Equal to your weight. That's what it's pulling you down with. It's always pulling you down like that. Just sometimes you have support forces countering it, or air resistance countering it. But whether I'm standing on the floor or up in the air, it's always pulling on me with my weight. What's it? Force. Yeah? Technically, they are a... You see how when you multiply mass in kilograms times an acceleration in blah, 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 a kilogram... Well, let me write it. You'd get... And that looks big and scary, and it happens a lot. So scientists said, hey, we're going to call that a newton. That's what a newton is. It's a kilogram being accelerated at so many meters per second squared. But who wants to say that every time, I guess. So. I wanted to mention, oh, I had it over here. Couple logistics. Remind you that the homework on chapter 4 and 5 is due Friday. We'll be through chapters 4 and 5 then. We'll review on Monday, and your test is next Wednesday. And the exam, I know you all want to know, as I've said before, it's going to be multiple choice, right here. And the questions are going to be just like what you've been seeing. I'm going to take them from your homework, the example problems in the text. There's hordes of questions at the end of the text. Wink, wink. I'm going to look right at those. And this author also provides the instructor with a test bank, which are just like from the book and WebAssign. So it's going to be the same feel and type. And they're going to be conceptual like this. So that'll be next Wednesday. So I strongly encourage you guys to, well, I sure hope you've at least read this stuff, but review this weekend. Come with some good questions. Make Monday useful for you. That way you can do better on the test. We'll try to get any holes and problems or anything I feel like I skipped over or didn't explain well enough Monday. Also, I just before class posted an announcement on WebAssign, so you can go there when you forget this. But Yashin is our teaching assistant. She's who's helping me grade your homework. She has told me, oh, sorry, that's my code. Thursdays. Every university seems to, I think the first university I was at, that was Thursday. Another one was this one. And another one it was TH, whatever. There's no confusion that way. She will hold office hours Thursdays from 3 to 4, if that works for you. Her office is again, posted in the syllabus online, which was, I said I didn't write down here. This building, room 209, desk 7. But remind you that you can contact her, and especially me, and if we need to meet, we'll make it work. Call me, email me, I'll meet with you if you need to. And on that vein, several more people have been contacting me through WebAssign. It's more efficient and straightforward, just straight email. Because I noticed it happened with 3 or 4 people now. They've sent me a message through WebAssign and then end up asking me later the same question because they never saw my reply. They didn't go back and look. Because there's 2 ways to contact me through WebAssign. You ask your teacher in the assignment that you're in. That's where you have to go back to see the reply. Or private messages. Well, it's just send me an email directly and we can cut through all that and not have that problem. So if you think I haven't replied to you, go check there because I sure thought I did and hit all the right buttons. All right. And I had another good question that will help us teach a point. So did you happen to read up on the water slides?
No, I was going to ask you after.
She had a great question. Comes up in my head periodically and then I forget the answer. Water slides. What do you notice about big people and little people on water slides? Have you guys been unbeknownst scientists and made observations? Big people go faster. That's what I'm getting at. Yeah, I tend to notice that too. Now, I'm going to preface all this. Lots of things are going on. And that's why it seems like everywhere I read there's different answers. But you can just go watch and trying to keep things constant. Just somebody being bigger and somebody being smaller. The bigger people tend to get to the bottom quicker. Well, why is that? Because I thought I was just telling you, you drop something big and you drop something small. I thought everything accelerates at the same rate. So what else is going on a water slide that you think are going to muddy this up?
Well, there's friction not only from the slide itself, but also from the water that's acting on the small body.
Yes. Anything else? He took all yours, huh?
The downward force is greater than the mass.
That is true. The downward force on the larger person is greater. Do you remember that? The force is greater. The force of gravity is the weight. It weighs more. Why is the force greater on the larger mass? Okay, there's air resistance too. That's not why, though. There's a support force too, yeah. Take these two. Oh, forget the water slide. There's a greater force acting on the medicine ball than the rope. I hope you guys aren't being too confused. But wait, they hit at the same time. I thought we just went through all this. Yes, this is heavier. It has more weight. There is more force. Why? Gravity's pulling, but it's pulling on this one too. Whose law is this? Which one? Yeah, this is leaning more towards the first. That's what I think you're saying. I just haven't heard the word inertia yet. Because this has more mass, it has more inertia. It resists change. So in order for these two to have the same acceleration due to gravity, that we see. We observe that. They're accelerating at the same rate. Since he's got more inertia, more mass, it takes more force to change his motion to the same acceleration as the light thing. That was this game. Both G. A. What is that? That's an F over an M. If that's the medicine ball, let's make that the rope. Then the medicine ball is, the ratio stays the same. That's why they hit the ground at the same time. They accelerate at the same rate, but it takes more force for the bigger thing. So that was a good way to review that. So you are right. The larger person on a water slide, it is pulling in with more force. They do have more inertia, which is getting to what I think the dominating reason why they get to the bottom quicker. Because you guys mentioned them. We had resistance from the slide, we had resistance from the water, and we had resistance from the air. Those are all forces trying to oppose the force of gravity, right? Well, the big thing, big person, has more inertia that way too. And so everything trying to slow the people down, it has less effect on the bigger person. And so they end up, their net acceleration is larger. And they get to the bottom faster. All else the same. Yes?
So I can't remember if I read this in the book, but water and air are similar in the fact that they are both called fluid.
Yeah, air and water, blood, fluids, yes.
And so kind of the same idea of terminal velocity where it takes a greater force.
Yes, yeah, it's very, you can have a terminal velocity in air or water, yes. Yes. Your book has an example of two people in a parachute. Get caught again. I'm pretty sure they do. You know, I keep reading the online questions and all these other resources, and sometimes I forget which one was actually in the book and not. But anyway, I'm going to share it with you anyway. Think of it this way. It might be a little easier. We got a big person, several coffee filters, and a little person. And they're going to go jump out of an airplane and they open their parachutes. The parachute's going to allow their velocity to reach terminal velocity, which means the net force is, right, 0 once they get to terminal velocity. Well, who reaches the ground first? The big person with the same exact parachute as the little person with the same exact parachute? I haven't even tried this. Let's see if it works. We have several. Yes. They both are feeling the same air resistance, the retarding force. But the bigger one has more force down. So the net force on the big person is larger, isn't it? Do you see that? So if the net force on the big one is larger, he'll accelerate greater. And whose terminal velocity will be faster? They both eventually reach terminal velocity and no longer accelerate, but the big person's terminal velocity will be faster. So they'll hit the ground harder. But I think it's the same gist on a water slide. They still have the same effects and everything on, but I think their terminal velocity, if you will, is a little bit greater. And so they reach the bottom quicker. Questions?
I've essentially done that on the log ride at the lagoon.
Yeah?
Myself, I'm 250, my buddy's 450, and his wife's his ex-wife's larger, and we went down and we got a standing ovation because of the way we made it.
Great. Well, yeah, once you impact, we're going to get into collisions with momentum and energy after the test. Yeah, impart that to the wave. Cool. And you guys were blowing everybody out, I'm sure. You'd beat me. Now, true, I want to specify, you can have a better bodysuit so there's less friction between you and your skin and the thing, and you can be aerodynamic, and you can make less contact by arching your back and all this stuff. And the skinnier person can beat the larger person. But that's for other things, and it's getting too complicated. But if they're just going down willy-nilly like most people do, we generally see that the larger person gets down first because he gets up to a greater speed. I find that very interesting. And we can thank her. She reminded me of that problem, and I reviewed. Okay, Newton's third law. I want to start it. May I have 2 volunteers, please? I won't hurt you. Great. Why don't you get on this one, you get on this one. We'll face each other, sit. It'll be safer. Sit. Crisscross applesauce. Yeah. Get to the edges, face each other. Wait. All right. Newton's third law. Here we go. We're going to get you guys together. And I want you to act like a wall, okay? Put your hands up and act like a wall. So your job is to try not to move, resist any change. Your job is to exert a force on this wall and push with your hand. Now, I told you not to push. Let's try it again. Okay, you can go ahead and put your hand up. It probably won't hurt her as much. Okay. But you're both, okay. Yes, I've done this before. Okay, this time you're the wall. Hold still. No. Can you hold still? Yeah. Okay, push on him. You're still moving. All right, push as hard as you can. Let's see if he can resist you. Can you scooch forward? Your arms are a little. All right, you're a rock. You're moving too. All right. Actually, we're not done, but this is proving my point. My point is they both move. They are trying to hold still. But when one person exerts a force on the other cannot help but exert an equal but opposite direction force on the other person. So that's why they both move. I'll bring you back together. All right, this time, maybe you can't push here. All right, you hold on to that so you're trying not to move. And can you push yourselves apart? And again, you recoiled a little. That's good. And it works. Thanks. You're good. It works whether you're pushing or pulling. This time you just hold firm, and you pull. And they both move. And my favorite way, though. Don't hurt her, okay? We'll have her start. All right, the job here is this thing's heavy. I want you to toss it to him. Not yet. You catch it. As soon as you catch it, be nice. Throw it back at her, and do that as fast as many times as you can. Go. Very good. Thanks, both of you. Now we'll make observations. I call these the push me, pull me carts. And it doesn't matter whether they push, they pull, or throw. Both of them are reacting, and I hope you saw that. Newton's third law is for every action, there's an equal but opposite reaction. It's in your book. That means if you, just what I said, if you exert a force on something, it exerts a force right back on you in the opposite direction. Same, equal in magnitude, opposite in direction. So no matter what they did, they both moved. Now, let's see how good a scientist you were. What else did you observe? She always went further. Very good. Can we explain that?
Yes, more mass. So it's going to take more force to get its inertia to the other part.
Excellent. This time, instead of keeping the A the same, the force is the same. It's the same force that he exerted on her as she exerted on him. But that was applied to two completely different masses. And no offense, I'm just using a big N. So who gets accelerated more? She does. And we saw that. Does that make sense? I love that, but that's because we can take Newton's third law and immediately explain these things because that would use Newton's second law. And Newton's second law made sense. Somebody, I think the first thing I heard was, oh, he's got more inertia. Right. So see, you just incorporated all three laws. More inertia means for the same force, he won't get accelerated as much because it resists that change in motion. That's how we got the second law. I love physics. It just helps me understand the world. That's Newton's third law. So, the book, as you read it, talk about some action and reaction pairs, which I think is useful. I didn't choose any homework on it, but I want you to understand them. There's always two forces, right? An action and a reaction. And the book emphasizes that it doesn't really matter which one's the action, which one's the reaction, because they don't exist independently. His push, well, she's immediately pushing back, whether she meant to or not, and vice versa. So pushing on the wall, I'm exerting a force on the wall. It's exerting a force back. And you know this now, I hope, because the net force on me is 0. I'm not changing my motion, I'm not accelerating, and we're not moving. So something must be countering my force on it, and that's the wall pushing back. It's a support force, just like you in your chair. They're equal, but opposite in direction. This too. It has weight. It's heavy. Down, force of gravity. The support force up is equal and opposite. And those are examples of action-reaction pairs. Force of gravity down. Oops. Come back to that one. That was what I was leading towards. Me on the wall on me. Action-reaction. Okay, now back to this one. Because this is the tricky one I was trying to get to. I just talking too fast. The reaction force of this is not the table. And this is how it can get confusing and why I want to do this. What's pulling this down? The earth, yeah, due to gravity. Very good. So the earth is what's pulling on this. So what's the reaction? It's pulling right back on the earth. Very good. The reaction force due to its weight is it pulling the earth up. Again, I'm about 175 pounds. That's a weight, that's a force. We like pounds, newtons, we can convert. That means the earth's trying to pull me down 175 pounds. I'm pulling on the earth with 175 pounds of force. Yeah. So next time you're feeling wimpy, just remember that. I am exerting a force on the earth with 175 pounds of force. So why, when I jump off the table, I remove a support force, woo, we see me accelerate. Why don't we notice the earth come up to meet me? Yeah. Its M is huge. And so, but technically, the earth does move about, that much. technically.
Did you say that there's a force on the other side of the Earth acting counter what you're doing?
Well, sure, you take my twin, I don't have one, and he goes 180 degrees around the globe, and he's standing over there. Yeah, I'm pulling on the Earth with 175 pounds of force this way, and he's doing it the other way. So the net force on the Earth would be 0, taking both of us into account. And since the Earth is completely covered with things, that's why one reason we don't see things. But it's also because even if it was just me, we wouldn't see the Earth accelerating toward me a whole lot, because it's just a huge amount of mass. But technically, it does move a little bit. Something better, the Earth and the Moon, more significant. They attract each other. The Earth's gravity pulls on the Moon's gravity pulls on the Earth, and they orbit around their common center of mass. The Earth is actually orbiting that too. It's just more like this, where the Moon is more like this. But that happens. And the way to remember that is an action-reaction pair, back to Newton's third law, they're always on opposite bodies. She exerted a force on him. He exerted a force on her. If we want to determine her motion, we have to look at the forces on her, not the force she exerted on him. Does that make sense? And vice versa. So in this case, if we want to determine the motion of this medicine ball, we look at the forces on it, which are gravity down, the Earth pulls on it, and the table pushing back on it. So your clue is, if you think, as I almost felt susceptible to, the table being the support force is the reaction, well, think about it. It feels the force down, this pushes on it, back up. That's on the same object. It can't be an action-reaction pair. They always have to be on opposite bodies. You follow that?
So if you took away the table, the ball will continually follow itself and opposing force acted on it.
Yes. Right. The reason it doesn't move, we want to note its motion. We look at forces only on it. The forces on it are
Gravity.
right, and the support force of the floor. They're both on the medicine ball. That's why its net force is 0, no acceleration, no change in motion.
So if you took away gravity, it would just stay where it was because the net force acting on the ball to keep it up won't change. Is that right?
It would just kind of float there. And if you gave it any impetus up, it would just kind of, because there's nothing pulling it back down. But I go, okay, Earth's pulling on that down. What's the reaction force? Due to Newton's third law, that's it pulling back on the Earth. See how one's on the ball, one's on the Earth. Does that help? That's what I'm trying to emphasize here. So when you're rereading or haven't read it, chapter 5, Newton's third law, we always say, for every action there's an equal and opposite reaction. Realize that has to be on opposite bodies. And if you want to determine the motion of just one of those bodies, only look at the forces acting on that body. Yes, you first.
So if you had two objects going through space and they flew next to each other, they'd essentially, if they had the same mass, would at the same time move towards each other?
Great question. Two objects similar going through space next to each other? Yes, because they have mass, they attract each other. So this one exerts a force on this one, and this one exerts a force on this one, and just like those two pulling the rope, they'll come together.
What if you had one that had a bigger mass than the other one?
And if this one's big and this one's teeny, let me check first. Who will exert a greater force on whom? They're equal. Newton's third law says it's equal. This one pulls on this one. Well, then this one pulls with an equal but opposite force on this. So it's the same force, but because this one's bigger, he'll be accelerated less. And so when they come together, I'll face you guys so you can see a little better. It'll be more like this. The smaller one will get accelerated more and move more. This one will move just a little as they come together. Just like we saw between these two. You were next, I think.
Yeah, so you said that there's a downward force of your weight due to gravity, and then there's an equal upward force of your, but But that doesn't make any sense because your weight due to gravity is 10 times more than your weight going up. Because gravity doesn't act upwards, so they wouldn't be equal. Because that's what weight is.
Tell me if I'm saying this wrong. The weight of this is Earth pulling on it down. Newton's third law says the reaction force is it pulling on the Earth up. You still agree with that?
Yeah.
Okay.
Although gravity doesn't act upwards, so the weight would be different.
Okay, there we go. Gravity, universal gravity, if we went out into space, gravity acts between two bodies with mass. We haven't covered this yet. It's later in the book, too. But we can cover it now because it'll help. Anything with mass attracts anything else with mass. And it attracts between the two objects. So if here's a mass and here's a mass, the direction of forces are like this. If the masses are over here, then the direction of forces are this way. They're always towards each other. So between this object and the Earth, they're this way. So for us on Earth, the dominating mass is Earth. So it's down. For Earth, it's trying to be attracted up from in our reference frame. Does that help?
Then we accelerated up at 10 meters per second squared as well.
We don't, because the Earth's pulling on us down. We accelerate down due to gravity. The Earth accelerates up due to our gravity.
And our gravity is
Minuscule, because our mass is puny compared to the Earth's.
so then how can the net force be zero?
The net force on what?
On our position and motion.
Good, yeah. Why is the net force on this zero then? Because if we want, net force is saying we want to look at the net forces just on this object. This object's being attracted down by gravity, the Earth. What else is acting on this object? The table up. That reaction force due to its weight is it acting on the Earth. But we're not interested in the Earth's motion to determine this guy's motion. Somebody over here? Yeah, orbits. Yeah, the book has a good chapter on orbits. A satellite going around the Earth, it's trying to fall, but at the same time it's falling. The classic example is a cannonball. If you fire a cannonball, gravity pulls it down. It's moving this way, but it's now got a force this way, and it hits the ground. Well, what if you shoot it faster? It'll go further, but then it starts curving around with the Earth, right, and eventually hits over here. If you can shoot it fast enough, it goes into orbit. It's like it's continually trying to fall to the ground and missing. That's what an orbit is. It's like constantly in free fall. That would be good.
I don't know if it's true or not, but I read once that they shoot the rockets that launch satellites at an angle that matches the orbit of the Earth. So wouldn't that in turn affect the Earth's orbit? Because it's a reaction against the Earth.
He said he read that they shoot rockets not straight out, but at an angle, kind of like what we just talked about, and generally the way it's rotating. Yes, because it's easier to overcome the gravity. Why fight it? But yes, if there's a force going up, then there's a force back. And technically, that does affect the orbit of the Earth. But again, we look at the masses and Newton's second law to see the effect. Space shuttle, mass of the Earth, big. And so the effect is negligible. But it is there. And they do need to account for it when they're trying to reach something far away and teeny like Mars, from our perspective. Great. We'll review some Newton's second law questions and more about Newton's third law Friday.